In this video, we're going to be looking at pure Year 1 mixed exercise from Chapter 5, question 18. This is on modelling with straight line graphs. So we have a scatter graph that shows the oil production P and carbon dioxide emissions C for various years since 1970. It's worth having a close look at the graph and checking that it makes sense, particularly which of the two variables is plotted as the independent variable along the bottom and the dependent variable up the side. Another name for the independent variable is the explanatory variable, the one that explains or determines the other one. And another name for the dependent variable up the side is the response variable, because that one responds to the original one. So we're not claiming that the more carbon dioxide is emitted, the greater oil production becomes. We're actually claiming the reverse of that statement. Essentially, the greater the oil production, the more carbon dioxide emissions increase. So it certainly looks like there's a strong correlation between how much oil we produce and how much carbon dioxide we emit. But it looks like the causal relationship definitely goes one way. We produce more oil and therefore more carbon dioxide is emitted. The question will work through a general process where they'll ask you, in this case, they're guiding you through quite nicely because they ask you to calculate the gradient by picking 2 points on the straight line and then to construct the linear model. And they even give you the relationship in the form C equals AP plus B. In other words, we know it's a linear model, but that basically means we're looking for a straight line type formula linking C and P. Interpret the value of A, so we need to make sense of what A means. And with reference to a value of B, comment on the validity of the model. So we need to look at exactly what the A and the B represent in this context. A being the gradient of our line of best fit and B being the y-intercept. Let's dive in. For part A, we need to identify a couple of points on the line. And the best way I can recommend you do this is to focus on the extremes. So look as close as you can to one end or the other of the graph. And we can see the most extreme point is going to be down here on the x-axis or the oil production axis. And if you look closely, you'll notice there should be something like 10 squares between 500 and 1,000. So 500 million tons represents 10 squares. So 50 million tons would be 1 square. We just have to go down 2 lots of 50 million tons from 1,000 million tons, and we get to 900 million tons. So I'm going to use that as one of my points. Bottom left line segment that's shown is the point 900, 0. I'm pretty confident with that one. Now we can look all the way up at the other end of the line, and we can see that at the most extreme end, which looks like it's going to be 5,000, we are just a couple of squares, or maybe a square and a half from the top. You don't need to be massively precise about this, but we've got an increase of 1,000 million tons, 1,000 on this scale for each square up. So if we start at 3,500 and go up 3.5 squares, we're going to be at 3,850. So at the top right, it's going to be at 5,000 and 3,850. That's about as precise as you're going to get. They will give you some leeway. I tend to be as precise as I can, but in the exam, they're not going to quibble over a small difference here or there. In particular, if somebody has decided to pick a point that looks convenient somewhere on the line because it's an easy point to spot, maybe somewhere in the middle, then that's also going to be fine. There'll be some variation in there. It's only a line of best fit that doesn't perfectly match the dots anyway, so we're not going to get too worried about the details within this. Now, it says use 2 points to calculate the gradient, so that's what we need to do. We're going to calculate the gradient. Remember, gradient means the change in y divided by the change in x. So we need to look at how far it's gone up, which is 3,850 minus 0, and divide by how far it's gone along, which is 5,000 minus 900. So if we work that out, 3,850 over 4,100 gives us a gradient of 0.939 to 3 significant figures. It might be worth putting an exact value in there as well, 77 over 82, but The approximate value, to be honest, is more sensible here because it's a mathematical modeling question. No one's claiming that for every 82 million tons, we emit exactly 77 million tons of carbon dioxide or whatever else that number might represent. It's an approximation, and this is pretty much what the number shows us. The linear model linking oil production and carbon dioxide emissions needs to have more than just a gradient, however. We need something approximating a y-intercept. Well, the easiest way to do this is to use the information we've already got. We've identified these 2 points. Let's use those points. If you've got a point and a gradient, then you are already set up for y minus y1 equals mx minus x1 curve. Y minus 0, for instance, equals m 0.939 times x minus 900. This is a nice quick way of generating a straight line equation. And all that remains, if you want to turn it into the format that they've asked for, is 0.939x, and then we need to multiply 0.939 by 900 to work out the constant that goes at the end. And I'm going to give that one to 3 significant figures as well. Comes out to 845.1 if you use 0.939. If you use 77 over 82, then it comes out as 845.12 something. I'm going to round it to 3 sig figs to make it consistent with the rest. There's one thing I need to change here, though, and that is the variables I'm using. I want to make sure that I'm writing it in the form they've asked me for, and if I've lost track of that because I'm concentrating on doing the question, I need to come back to that and say, well, yes, the vertical axis does represent carbon dioxide, and therefore y will be c. 0.939p plus, well, it's actually minus 845. You could think of it as add negative 845 if you like, where the value of b is technically minus 845. So that now is a linear model for the link between carbon dioxide emissions and oil production. And if we knew how much oil we were producing at any given moment, then we could connect that to carbon dioxide using this formula. So that was part B. We're now on part C, which has asked us to interpret the value of A in your model. This is the value of A. A is 0.939. In general, when you're asked to interpret values for a straight line, you need to think in terms of the definition of gradient and intercept. So the gradient tells you the rate at which y changes as x changes. We used it to calculate the gradient in the first place. But in this context, that means the rate at which c changes as p changes. So for every 1 increase in p, there will be an m, or in this case 0.939, increase in c. So this represents an increase of 0.939 million tons of carbon dioxide emitted for every additional 1 million tons of oil production. So take care to notice the units. The million tons is given on the graph, carbon dioxide emissions in million tons and oil production in million tons, so we need to make use of that. But an increase of 1 in the x direction, or the oil production direction, gives an increase of 0.939 in the y direction, or the carbon dioxide emissions direction. For part D, they're not asking you directly to interpret the value of B, but they kind of are. With reference to the value of B, comment on the validity of the model for small values of P. What B represents as the y-intercept, or in this case the c-intercept, is how much carbon dioxide we will be emitting if we had 0 oil production, because that's what the y-intercept is. So we're saying B represents, let's include our value of B so we know exactly what we're talking about, minus 845. This represents the number of millions of tons of carbon dioxide we would meant to be emitting if oil production was exactly 0 million tons is the same as 0 tons. So if we're not producing any oil, we would be emitting negative 845 million tons of carbon dioxide. Does that make sense is the question. Comment on the validity of the model is usually an indication that you need to look critically at the numbers. Sometimes you'll find that the number is kind of what you would expect, close-ish. It doesn't have to be perfect. We don't want you saying, oh, well, this predicts 140 and the answer was actually 143, so obviously it's nonsense. If it's close enough, then it's been a valid prediction. We always have error bounds. We have margin for error in any of these predictions that you might make. But if it's way off or if it gives suspicious looking results, typically negatives can be suspicious, plausibly you could imagine a scenario where if we're not producing any oil, perhaps there's enough absorption of carbon dioxide that we end up having a negative carbon dioxide emission. But it seems like a bit of a stretch given what we know about oil production and carbon dioxide. So having a negative is a bit suspicious here. I would say something like it is unlikely that carbon dioxide emissions could actually become negative. So the model is likely unreliable for such low values of oil production. Also, note that this would represent extrapolation from the known data. Anytime we're extrapolating, we know that to be dodgy ground. It's one of the most useful things you can do with data, but it's also one of the least reliable things you can do because we just don't know. Beyond the information we have, we cannot say what will come next. If we look at this graph, we could make some reasonable predictions here about what the emissions would be if we had 3.5 million tons, even if there's no data point at 3.5 million tons. But we can't make particularly reliable predictions about what happens for values lower than about 2 not talking about 3.5 million tons, I'm talking about 3,500 million tons. And if we go as low as, say, 2,000 million tons, we're starting to get to dodgy ground because we don't have data there. And if we go beyond 4,000 million tons, similarly, we don't have the data. In fact, from the uptick, more or less around 4,000, it looks like potentially the increases in carbon dioxide emissions might grow faster than a linear model would predict, even beyond that point. But we just can't say for sure because we don't have data beyond that. As usual, we go back and we check the question to make sure that what we've answered is what was asked. So in this case, the question gives us the graph linking the two things. We can see that our numbers more or less make sense. We're saying that there's pretty much a gradient of 1, and we can check the numbers to see that that seems to work. The graph goes along by approximately from 1,000 to 4,000, let's say, in this first section. And at the same time, it goes from 0 to about 30,000 there. Here we go, and here's where I spot my error. There we go. This is why we do this. That wasn't deliberate. It was a genuine error. When I was trying to identify the y coordinate up here, I wrote down 3,850 when actually I need an extra 0. So here we're going to go back and we're going to fill that in because this is a quick, easy fix. Okay, and this is why we do this. We've gone through the question, we've taken our time, but now we're doing a check. So that should, instead of 3,850, it should have been something 10 times bigger. And just checking to see if the gradient really is about 1 showed me, no, the gradient looks like it's more like 10. So maybe I've made a mistake. And as soon as you spot the mistake, often you identify how to fix it at the same time. So that means we've now got a correct answer here. And we're going to filter that through to see what happens when we incorporate that extra 0 all the way through here. And it's not too difficult to do. That extra 0 is going to increase my gradient by a factor of 10. And that means that this number to 3 significant figures is 9.39. And when I come down to this line, 9.39, 9.39. We've got to be a little careful at this point because that 9.39 doesn't just affect that number. When we do the algebraic step, it's going to affect this number as well. 9.39 times 900 is 10 times bigger than 0.939 times 900. So we've got a change here as well as a change here. When we get to the end, 9.39 minus 8,450 should now be a valid result. And of course, we're going to need to change a little bit what we're saying in here. So 9.39 for A means an increase of about 9.39 million tons of carbon dioxide for every additional 1 million tons of oil production. And then when we get to part D, the value of B needs to be bigger, minus 8,450. But all of our description, explanation of why that's invalid is still perfectly fine. So now you can see why it's useful to go back and make sure you double check. Often errors like this are easy to spot and easy to fix. It just takes the process of getting into the habit of going back and looking for the error and finding what might have gone wrong. Simple things to verify. Even if you don't think you've done it wrong, have enough humility and self-doubt that even though you're confident with the maths, you know that you're also human and you will occasionally mess up. And if you can find a way to mitigate for that as you do questions and after you complete a question, then you will be much less likely to end up with errors at the very end. Spot the errors before the examiner has the chance to, and everything will be fine.